Okay, so hello. First of all, I would like to thank the organizers for inviting me. So I will talk about laboratory astrophysics and interstellar ices. I tried to do quite a general talk by picking some of the recent results that I've seen, some experimental results. Of course, it won't be exhaustive and I won't be a specialist of everything. And I will also present the work done in the group in Lerma. It will be on the photo-induced processes and ices. It will be part of Romain Baselget's thesis under the supervision of Jean-Luc Fillon and Mathieu Bertin, and also part of Rémi Dupuis' thesis. And it's also a collaboration with the ICP and the ISMO. So there are lots of things that can happen to interstellar ices throughout their lifetime. So if we consider ices in a molecular cloud, they can be submitted to some non-thermal energy that can process them. And then if they evolve near a protostar, then they can be submitted to thermal energy and also have some processing. So in my talk, I will talk about these non-thermal energy processes and these thermal energy processes that are occurring on interstellar ices from an experimental point of view. So what are the non-thermal energy sources in the interstellar medium? So you can have photons, so either UV photons or X-ray photons. These photons can come from the background, typically the interstellar radiation field, or directly from the star. And you have more or less photons that can penetrate into the interstellar object, the molecular cloud, or the protoplanetary disk, for example. And you can also have another source of non-thermal energy, which are cosmic rays that are present almost everywhere. And for example, if we consider cosmic rays into a molecular cloud, they can also generate some UV photons. So there are many insights from observations. Here I'm talking about gas phase observations. And especially with the resolved observations, you can really hint into some physical processes happening into interstellar ices. So for example, here, it's been an observation of a hot core with some complex organic molecules, and you have a change in the abundance when you consider different temperatures in this hot core. And they propose to explain these different abundances with different physical processes, either gas phase processes or non-thermal processes, so that are released from the ice into the gas phase. There have also been some observations that are spatially resolved in protoplanetary disks. And if you perform a model to explain the observation, so the observations are in blue and the model is in black, you see that with only gas phase reactions, you cannot explain the observation. So you really need a full network. So you need to include solid phase reactions to explain the gas phase abundances. So you really need these solid phase processes. And it's also true for PDR regions, as it was shown by Vivenia Guzman and co-authors in 2011. So in order to interpret observations and to perform astrochemical models, you need to obtain laboratory data. So you try to be as close as possible to the interstellar conditions. And how do you perform a study on ices? So first of all, you need to build your ice in your experiment. So you start from molecules in the gas phase, they stick onto a cold substrate, and then you build an ice. We will hear about this sticking problem to substrate in Philippe Parent talk. And then once you have your ice, you can study it. So you can warm it up and detect molecules in the gas through mass spectrometry, for example. And you can study some irradiation processes. So for example, with photons that are more or less similar to interstellar photons. So you can use a laser, LAMP, synchrotron, or you can also want to study the effect of cosmic rays by studying accelerated ions. And then to characterize your irradiated ice, you can use gas phase detection with mass spectrometry, chromatography, or you directly probe the solid phase with infrared or electron paramagnetic resonance. So in my talk, I will divide it in two parts. The first part will talk about thermal energy processes in ices. And the second part will deal with non-thermal energy processes. So I will start with thermal energy processes. So that is when you heat your grain, you heat your ice, basically. So you can have thermal desorption and also diffusion. So just a very few words about thermal desorption. So it consists in, first of all, it's useful to determine snow lines locations, to interpret astronomical observations, and to build nice astrochemical models. So from an experimental point of view, you just heat your ice and you record the molecules that are desorbing from the ice, that are escaping the ice surface, that go into the gas phase, and you record that gas phase signal as a function of the temperature, and you have some temperature program desorption results. And you can see Francesca Kruszkiewicz poster if you want more information into this technique. And I just want to highlight a recent review on thermal desorption by Marco Minisale and co-authors. So they really make a complete review of this process. And in this review, there is a list of recommended values that are used to describe the thermal desorption, which is just an Arrhenius law. And they recommend the value of the prefactor and value of the binding energy. So that's just to describe the thermal desorption process. And they try to give as precise values as possible. So the simplest way you can do it is just consider a single binding energy per molecule. But then the reality is more complex, not just one energy, it's a whole distribution of energy. So it's better if you can consider this whole distribution of energy, and they really listed the literature values here. So why is it important to take distribution of binding energy, as it was suggested in this paper from Misha Doronin 2015? It's important because it has really a strong impact into the interstellar abundances. So you can show that here. So this is a simulation that was performed in dark clouds. And so this is the abundance in the ice of some species as a function of time. And what they changed is the binding energies. So they put some uncertainties into the binding energies. And then you see that it creates a massive change in the ice abundances. You have 8 orders of magnitude variation here. So it's really huge. And not only the abundance changes, but also the profiles. It's quite hard to see because there are so many curves, but the profile is not the same when you change the binding energy. So it's better to use as precise values as possible, and for experimentalists to give as precise possible values of these binding energies and the prefactors. So now very just a few words about another thermal energy effect, which is diffusion. So molecules are not static, they move a little bit. And as you increase the temperature, they will move more and more. And so if you have a lot of diffusion, you can have a lot of molecular complexity, a lot of chemical reactions into your ice. So this is important to understand these diffusions. And the problem is that there is no experimental data. So what is usually done is that the diffusion energy that is considered is a fraction of the adsorption energy. And this fraction is taken as constant for every molecule that you consider. But recently there was a nice experimental study by Furuya 2022. So they wanted to study this diffusion process, this surface diffusion process, And they used some microscopy technique. And they studied various molecules. You have the list here. So it's molecules that are adsorbed on water ice. And what they found is that the diffusion energy is not a constant fraction of the desorption energy. So you really have a change here from 0.2 to 0.7. So it depends on the surface species. So that's an interesting result. And I guess that they will do more studies afterwards. Okay, so now I will switch to non-thermal energy processes. So we will look at the effects of the cosmic rays or of the photons onto the ice. So it can create, for example, dissociation of the ice molecules, chemistry, or it can also create exchanges from the solid phase into the gas phase. So that's called desorption. And there is also one non-thermal process, which is chemical reactions that occur into the ice, and then that leads, that gives a new molecule that can escape the ice and desorb. And I won't talk about that. There are only very little experiments. You can look at Marco Minisale paper from 2016 if you want to hear more about this chemical reaction desorption. So I will start with the cosmic ray effects. There was an experimental study to mimic the cosmic ray effects using accelerated ions. And cosmic rays can really change the ice in different ways. First of all, it can change the ice structure. So this is a study performed by Emmanuel and co-authors. So they started from crystalline ice. They used some accelerated ions, and they shown that it changes the ice structure. You don't have crystalline ice anymore. You have an amorphous ice. So cosmic ray analogs change the ice structure. And then another effect of cosmic ray. So here they studied water ice. And they studied the water desorption from the water ice. So actually it's called the sputtering. It's really a lot of molecules that get out from the ice. Here you see the efficiency of this cosmic ray analogs sputtering. So for one accelerated ions, you have 10 to the 4 water molecules that get out from the ice. So it's really very efficient. And in this paper from Emmanuel 2018, they did a thickness-dependent study. So they changed the ice thickness, and they showed that you have some variation of the desorption yield. It's really a fine study, which is interesting to take into account into the astrochemical models. And we will hear more about the astrochemical modeling of non-thermal processes, including cosmic rays in Angèle Taillard's talk. Okay, so now I will switch to photons effects. So photons, they can create some chemistry into the bulk of the ice. So here I wanted to highlight a result from Gutiérrez Quintanilla 2021. It's from Marseille, from the PIN. So they studied an ice containing organic molecules. And what they wanted to see is the chemical reaction network, try to unravel this network as precisely as possible. So they started from methanol ice. They radiated it with UV photons. And then they wanted to identify the radicals that were created because of this UV irradiation. So to do that, they used infrared spectroscopy, but also EPR, electron paramagnetic resonance. This is quite a new way of new technique, I think. And with that, they could identify some radicals into the ice. And then there were some chemical reactions occurring between these radicals. And so these chemical reactions led to the formation of complex organic molecules. You have a list here: methylformate, glycoraldehyde, ethylene glycol, glycoroxide, and so on. And so this is a study that showed that radical chemistry can lead to complexity, to complex organic molecules formation. Okay, so now I will switch on to the last part, which is the study of UV photons onto the ices, but that leads to some gas phase exchange that is called UV photodisruption. So that's the disruption of molecules from the ice into the gas phase due to UV photons. So this is a study performed in the SPICE setup, which is surface processes on ices at Lerma. So you have a picture of the experiment here. So I will talk about the acetonitrile ice, which is a recent study published by Romain Basalget. So first of all, we did the acetonitrile ice into a cold substrate. Then we put some far UV photons that come from the solar synchrotron. And then we look at the molecules desorbing from this ice through mass spectrometry. And what we want to do is a quantified experiment. That means to know how many molecules desorb from the ice. So we have a way of doing that. And here we obtain the photodesorption yield. That's this number of molecules that desorb from the ice per incident UV photons. So you see that it's in the 10 to the minus 5 molecules per incident photon range. And we can do that as a function of the photon energy, because at solar synchrotron, you can change the incident photon energy. So this was published by Romain Basalget last year. And so what we saw is that CH2CN, so the acetonitrile, the parent molecule desorbs, but also some fragments. For example, here you see CHCN. It's not only this one. We have a whole list of desorbing fragments, CHCN, HCN, CN, CH3. So the first thing that we can say is that we have some dissociation of these molecules. That's some process that is important. And then in order to use this data in astrochemical models, it's good to give what we call the average photodesorption yield, astrophysical photodesorption yields. So that can be used in several astrophysical environments. For example, here in the ISRF, or here in dense clouds or disks. So you see that there is a small effect of the environment if you compare the two columns here. And then these numbers can be implemented in astrochemical models and can improve the fitting of the observational data. So I've told you that acetonitrile desorbs, but also some fragments. And why is it important to take into account all these desorption products, including the fragments? It's because dissociation is an important process that can have some impact into the astrochemical modeling. So here is a study from Lingeric and co-workers. It's Catherine Walsh model. So here it's not acetonitrile, it's methanol, but the idea is the same. So she modeled the methanol gas abundance and the methanol ice abundance in a protoplanetary disk. And she studied different cases when the methanol dissociates. So here, when the methanol dissociates and when it doesn't dissociate. And you see really changes in the abundance that are obtained, either in the gas phase or in the ice. So it's really important to take into account as accurately as possible all the processes, including dissociation. I also wanted to say that we studied the CH2CN ice, which was pure, but also a mix with CO. And what we found is that there is no strong influence of the CO matrix into the desorption yields. This is quite different from what was obtained with methanol ice. This was published by Mathieu Bertin in 2016. So in this case, there was a huge effect of the CO matrix into the desorption of CH3OH. So here is a summary of what different studies that we performed with the SPICE setup in the last 10 years. So we studied small molecules, diatomics, like CO and 2NO. And this, so here it's the photo desorption yield. So it's quite efficient for small molecules like CO and 2NO. It's less efficient for larger molecules, but still it's not exactly the same for CH2CN or for CH3OH. And then it's like intermediate for CO2 and CH4. So what is usually done in astrochemical models when there is no yield available is that the value 10 to the minus 3 is used. So default value. And the problem is that it's not good for every molecules. So what we would like to do is to try to predict photo desorption yield for any molecules. And this is a part of the ANR Pixies led by Mathieu Bertin. And to do that, it's really important to understand the photo desorption mechanisms that are at play in ices. So I just show here an example. The problem is that the desorption mechanisms are known for just very, very few systems. And here we could unravel the desorption mechanisms for model ice, in which there is water and an adsorbate above. And with UV photons, the hydrogen atom dissociates from the water molecule, and it's like a small bullet. It just goes away up to the surface. And then if it encounters an adsorbate, it can kick out the adsorbate, and you have the desorption of this adsorbate. And what we've shown is that if you have a light adsorbate here, like argon or CO, it just goes easily into the gas phase. That means you have a high photo desorption efficiency here. Whereas if you have like a strong heavy one above you, it's quite hard to put it into the gas phase, so it's less efficient. So you have a correlation of the photo desorption yield with the transferred kinetic energy between this hydrogen collision with the adsorbate, and it was published in this paper by Dupuy in 2021. And we've also studied water ice, and we've shown that there is another mechanism that is at play, which is some photochemistry occurring in this ice. So UV photons, they dissociate water molecules, and then you can have some reactions between the radical from one molecule with another one from another molecule. And that's some exothermic reactions that can lead to the desorption of water, and it was published by Jean-Luc Fillon in 2022. And I think I'm done. Okay. So please listen to Samuel Delfray's talk to understand all these energy transfer mechanisms in ices. Okay, it's finished.